Hello. Today we are starting section 6 in our um, notes, and we're going to be talking about modeling direct variation. Yesterday we just learned how to graph a line in slope-intercept form, and so today we're going to branch off that and talk about direct variation. Our learning target today is to write and graph direct variation equations. So hopefully by the end of the day we should all be able to write and graph those direct variation equations. We have two new vocabulary words. The first one is direct variation. It's when two variables are, they show direct variation if y equals ax and a is not 0. So this direct variation equation looks a lot like our linear equation in slope-intercept form, but instead of y equals mx, we have a. Why is that? Well, our next vocab word is our constant of variation, which is that a that we were talking about earlier. So the non-zero number a is called the constant of variation in a direct variation equation. And then when we write this equation, y equals a times x, or y equals your constant of variation times x, y is said to vary directly with x. So if you notice, this would be like our slope-intercept form where your slope is a, or m equals a, and your y-intercept then is 0. Okay, so if we were to go ahead and try one of these examples, um, let's say we have a Snickers bar. Everyone likes Snickers. They cost 75 cents each. If I purchase some candy bars, the total cost, or C, of my purchase varies directly with the number of candy bars I buy. So basically, what I'm saying is if I buy one candy bar, I know it's going to cost 75 cents. If I buy two candy bars, I know I'm going to pay the same price, that 75 cents, for each one of those candy bars. So now I've spent $1.50. And what that means is that the amount in which it varies is a multiple of that 75 cents. So if I buy two candy bars, I multiply that 75 cents by 2. If I buy 3, I multiply 75 cents by 3. If I buy 5, I multiply that 75 cents by 5. So we're going to create a table here to help us graph this direct variation equation and to come up with an equation. Okay, so let's say we have on our x, or our input side of the table, we have n, since, oops, that's our number of candy bars. And on our y side, we'll have our c, or our total cost. If I buy one candy bar, I know my total cost is going to be that 75 cents. If I buy two candy bars, I know my total cost is going to be $1.50. If I buy three candy bars, now my total cost is going to be $2.25. We'll do just a couple more. If I buy four candy bars, add 75 cents to the previous total, which was $2.25, and I get $3 even. And if I buy five candy bars, I'm going to pay 75 cents for each of those five candy bars, so my total is going to be $3.75. Okay, so now I've created this table of inputs and outputs, or my number of candy bars on the left here and the total cost on the right. We can go ahead and graph this equation, or graph these inputs and outputs. Oh, and we forgot a very important one, so we'll add it now. What if I didn't want to buy any candy bars? What if I bought 0? How much am I going to pay? Well, we would hope we just pay $0, and that's exactly right. If you're not buying any candy bars, you're not going to pay anything. So we're going to have a point here at 0, 0. We're going to have a point at 1 and 75 cents. So we're thinking of our n is going to be like our x-axis, and our c will be like our y. So if we have 2 candy bars, we'll have $1.50. 3 candy bars, we're at $2.25. 4 candy bars, $3, and so on. And I can draw a line to go through each of those points. However, we need to talk about the values that our number of candy bars can be. Can we have 0 candy bars? Sure, you can go into a store and say, yep, I'm not going to buy any candy bars. That would be 0 candy bars for $0. Can we go into quadrant 3 down here and have negative candy bars or spend negative money? And no, we can't do that. You're not going to go in and buy negative candy bars and you can't spend negative money. So, oopsie, I don't want that line. So the line that we want is going to start at 0, 0 here and go through each of those points. Now we can buy as many candy bars as our little hearts desire, and our cost will just keep increasing. So there's an arrow on this side and there's not an arrow on the other. And we can create an equation for what we've just found. So on our n here, we are just adding 1 each time. And on as far as our cost, we are adding 75 cents each time. All the way down. So since we're talking about direct variation, our constant of variation, or that, think of that like your rate of change or your slope. It would be similar to your slope. So in this case, we're going to have C equals, and our constant of variation, or our rate of change, is 0.75 or 75 cents for every 1 candy bar. So we have 0.75 for every candy bar, which we said was n, the number of candy bars. So again, we have a rate of change, and we don't have our y-intercept is 0. So we don't need to write a y-intercept. And we can see that in our equation. Okay, let's try another one. We have a little note up top that says, notice that a direct variation equation y equals a times x is linear in slope-intercept form with m equal to a, and b is 0, or our y-intercept is 0. The graph of a direct variation equation is a line with a slope of a and a y-intercept of 0. So the line passes through the origin. So basically, if you have an equation and it's linear and it passes through the origin, this is a direct variation. Any linear equation that goes through the origin is a direct variation. So looking at the example below, y equals 2/3 x and y equals negative 3x, both of these have a y-intercept of 0. There's no constant term. And they have a slope of 2/3 and negative 3. So that means y is varying directly with x. If we graph these, we just learned how to graph in slope-intercept form yesterday. And so we know that we can add plus 0 here to both of these. And of course, we wouldn't write our direct variation with plus 0 because it's not necessary. But this tells us that our y-intercept is at 0. So we're going to make a point there at the origin, 0, 0. And then we're going to use our slope to graph the rest of the line. We remember our slope is rise over run, so this is 2 over 3. So we're going to rise 2, because it's positive, from our y-intercept, rise 2, and run 3, that's also positive, so we're going to the right. There's our point. We're going to rise 2 and run 3. We can also do exactly the opposite. If this was a negative 2 over a negative 3, we could go down 2 and to the left 3. And this is all along the same line. In this case, there's no value that x can't be, so we would just go ahead and draw a line through all of our points, and we have our direct variation, the graph of our direct variation equation. we can do the same thing over here. We start at 0. And we know that if we have a slope of an integer, we can just write it over 1. And so we're going down 3 and to the right 1. Or just the opposite, up 3 and to the left 1. Either way it works. And so we go ahead and draw a line through those points. Arrows on both ends. Oop. And we have the graph of our direct variation equation there. Okay, let's try another example. What if we need to write and use a direct variation equation? So if I actually need to write a direct variation equation, that's a lot like the Snickers example we just did. So we're going to try that again with a different example using a graph. Okay, so if we're given the graph, we need two things. We need our y-intercept from our graph, and we need our slope, or our constant of variation in this case. So we know it's going to be y equals, and if this is already telling us this is a direct variation, we know our y-intercept is going to be at 0. We already know that. Plus we can see on the graph. So we just need to find our slope. So I'm going to draw my slope triangle. I'm going to go up 2 and to the right, or excuse me, up 2 and to the left 1. So that means this is going to be -2 over 1 times x. And we don't need to write that over 1. We could just write this as y equals -2x. So if we're going to find the value of y when x equals 30, all we do is we substitute in 30 in place of x. So -2 times 30. And we get y equals -60. So what that's telling us is if we were to go ahead and graph a point when x is 30, way over here, way off our graph, it's going to be way down at a y value of -60. All right, we're going to try one more. For this problem, we have a saltwater aquarium, and the number S of tablespoons of sea salt needed in a saltwater fish tank varies directly with the number W of gallons of water in the tank. So we're mixing salt and we're mixing water to create the right mix in order to keep these saltwater fish alive. The pet shop owner recommends adding 100 tablespoons of sea salt to a 20-gallon tank. So we need to write a direct variation equation that relates W and S. So what we're missing here is our constant of variation. We know that we have W, our gallons of water, and we have S, our tablespoons of sea salt. We need to solve for that A. All right, so to answer that first question, we need to set up an equation that relates salt and water. So we're going to set up S is equal to A times W, or the amount of salt is equal to the constant of variation multiplied by how much water you have in your tank. And in this case, we have 100 tablespoons of salt equal to, we don't know our constant of variation, times our 20 gallons of water. And then we just solve for A, so we're going to divide both sides by 20. When I divide 100 by 20, I'm going to get A is equal to 5. So now I'm going to use that value I just solved for to write that equation that they were asking for in this first question. So I'm going to substitute in that 5 for A. So I get S equals, not A, 5 times W. I'll write it like this. And so that tells us that whatever gallon tank we have, we can figure out how much salt water is needed. So for the second part, how many tablespoons of salt should be added to a 30-gallon fish tank? I'm going to substitute in 30 for my water, the gallons of water. And when I multiply 5 times 30, I get 150 tablespoons of salt that I need to add to that tank in order to keep those fish alive. All right. I want to make sure that you check over your homework from yesterday. So we're going to get that out quickly. Go ahead and just pause the screen here. Correct those problems and mark your total at the top. Go ahead and turn it in. And then you can get going on your homework that's listed in Schoology. And hopefully we can all model direct variation, since that was our goal today, to be able to write and graph those direct variation equations. Just remember, direct variation is when um, you have a slope, so a linear equation, and your y-intercept is 0.